The energy that powers our civilization is on the verge of a total transformation. We are about to explore 24 revolutionary concepts that promise endless power, from cosmic arrays that capture the sun's full fury to devices that pull fuel from the air itself. By the end of this journey, you will possess a complete mental map of the future energy landscape. How will we harvest power from the silent, frigid depths of the moon? And what immense structure could one day encircle a star? The answers reveal a future where scarcity is obsolete. What does a world of true energy abundance feel like to you? High above our planet, a fleet of silent sentinels could one day harvest the sun's pure, unfiltered light. These are not ordinary solar panels, but vast orbital arrays designed to capture energy where the sun never sets. Unhindered by weather or the cycle of day and night, they convert this constant stream of sunlight into either microwave or laser beams. These invisible energy signatures are then transmitted with pinpoint accuracy to receiving stations on the ground, known as rectannas, which convert them back into electricity for our grids. The core advantage is sheer consistency. As Dr. Paul Jaffe of the U.S. Naval Research Laboratory points out, a single geostationary satellite could deliver power over 99% of the time, a reliability ground-based renewables simply cannot match. This vision hinges on two critical advancements. First, the solar collectors themselves must be incredibly lightweight and efficient to be launched and deployed economically. Second, the wireless power transmission must be both highly efficient and completely safe. How do you ensure a powerful microwave beam only energizes its intended target and poses no risk to aircraft or wildlife? Researchers have made remarkable progress. Japan's space agency, JAXA, has already demonstrated the precise microwave transmission of power over a distance of several dozen meters, a crucial proof of concept. The path forward involves scaling this technology to orbital distances while implementing robust safety systems that can instantly shut down or redirect the beam if anything strayed into its path. While the initial costs are high, the promise of a truly continuous and massive clean energy source makes this celestial ambition a serious pursuit. This idea of drawing immense power from above finds a fascinating parallel in a concept that taps into the profound cold waiting just next door. Our planet's silent companion holds a treasure locked within its dusty surface, a potential fuel so potent it could redefine energy itself. This is helium-3, a rare isotope of helium that has been deposited on the moon for billions of years by the solar wind. Here on Earth, helium-3 is incredibly scarce, but on the airless moon, it is sprinkled liberally across the vast lunar regolith. Its value lies in its potential for nuclear fusion. Unlike other fusion fuels, fusing helium-3 atoms promises a reaction that releases enormous energy while producing virtually no long-lived radioactive waste. It is the dream of a perfectly clean, profoundly powerful energy source. According to fusion researcher Dr. Gerald Kolsinski, the numbers are staggering. Just 25 tons of helium-3, a volume that could fit in a single space shuttle cargo bay, could theoretically supply the entire United States with energy for a full year. Unlocking this resource would require a permanent industrial presence on the moon. Imagine autonomous rovers scouring the gray plains, scooping up the top layer of soil. This regolith would then be heated in specialized processing plants to release the trapped helium-3 gas, which would be collected and compressed. The refined fuel would then be launched from the moon's low gravity back to Earth. This entire enterprise hinges on two monumental developments. First, we need to dramatically lower the cost of space travel. Companies like SpaceX are actively working on this, with fully reusable rocket systems that could one day make Earth-Moon cargo routes as routine as international shipping lanes. Second, and perhaps more crucially, we need to master nuclear fusion technology here on Earth. The fuel is useless without the engine to burn it. This vision of a lunar mining colony inevitably raises profound questions. Who owns the resources of the Moon? The Outer Space Treaty of 1967 states that no nation can claim sovereignty over celestial bodies, but it says little about commercial exploitation by private entities. Does harvesting the Moon's riches for one planet's benefit set a precedent for a new era of cosmic resource wars, or could it be managed as a shared inheritance for all humanity? The answers will shape our future as a spacefaring civilization. This quest to draw power from our nearest celestial neighbor is just the beginning. What if we could build an energy source so vast it completely envelops its creator? The ultimate expression of energy ambition is a structure so vast it defies conventional engineering. A Dyson sphere represents the logical endpoint for any civilization whose hunger for power outgrows its home planet. Rather than a solid shell, which would be mechanically unstable, the most plausible design is a Dyson swarm. This involves millions of individual solar collectors, each in its own independent orbit around the star, forming a vast, thick cloud that intercepts nearly all the sunlight. Physicist Freeman Dyson, who popularized the idea, noted that the infrared waste heat from such a civilization's activities would be its most detectable signature from across the galaxy. This very principle guides astronomers today as they scan the cosmos for unusual stellar dimming patterns that might indicate the presence of an alien megastructure. Stars like Tabby's star, which exhibited erratic and significant drops in brightness, sparked intense speculation about possible alien engineering, though most scientists now attribute the phenomenon to vast clouds of cosmic dust. Building such a swarm would require a mastery of materials science and robotics we can barely conceive of. The initial construction would likely be undertaken by self-replicating robotic factories. These machines would be sent to a nearby asteroid belt, where they would use local resources to build copies of themselves, and then begin constructing the first power collectors. Over centuries, this autonomous army would exponentially multiply until the star is gradually enclosed. The energy harvested would be almost incomprehensible. Capturing just 1% of our sun's total output would yield roughly 10 trillion times more power than all of humanity currently uses. This is not merely for lighting cities, but for powering computations on a galactic scale, or for accelerating starships to a fraction of the speed of light. The coordination required is a challenge that spans generations. How would a society maintain the collective will and organizational stability to see a project through that might take longer than the entirety of recorded human history? It invites us to consider our own species' long-term trajectory. Are we destined to eventually become the builders of such cosmic wonders, or are we merely laying the groundwork for the artificial intelligences that will ultimately inherit the stars? This vision of harnessing a star's full might forces us to look back at our own world, where other revolutions are brewing not in the void of space, but in the very air we breathe. While we contemplate structures that could encircle stars, our own planet holds a massive, untapped battery operating on a simple principle of physics. The ocean itself is a vast thermal engine where the sun-warmed surface water sits atop the frigid depths, creating a constant natural temperature difference. Ocean thermal energy conversion, or OTEC, is the technology designed to harness this gradient. It works on the same basic principle as any heat engine, but instead of burning fuel, it uses the warm surface water, typically around 25 degrees Celsius, to vaporize a low boiling point fluid like ammonia. This expanding vapor spins a turbine to generate electricity. Then, cold water pumped up from depths of around 1,000 meters, often just 4 degrees Celsius, condenses the vapor back into a liquid, completing the cycle and allowing the process to begin again. This cycle runs continuously, 24 hours a day, 7 days a week, offering a rare prize in the renewable world, base load power that does not depend on the sun shining or the wind blowing. Dr. Luis Vega of the University of Hawaii has championed this technology, pointing out that OTEC plants could provide stable, reliable electricity for tropical coastal regions, drastically cutting their dependence on imported fossil fuels. The potential benefits extend far beyond kilowatts. The cold, nutrient-rich deep seawater brought to the surface is a resource in itself. It can be used for sophisticated aquaculture, cultivating valuable fish and shellfish, or for cooling buildings in a process known as district cooling. The process of vaporization and condensation also naturally produces a significant amount of desalinated water, a precious commodity for many arid island nations. The proof of concept is already floating. The Natural Energy Laboratory of Hawaii Authority has hosted experimental OTEC systems for decades, demonstrating the technical feasibility and spinning off successful aquaculture businesses in the process. Yet, the path to widespread adoption is blocked by immense engineering and economic hurdles. Constructing an OTEC plant means building a massive floating platform, a small industrial island, equipped with enormous heat exchangers and a colossal, flexible pipe that descends as deep as the Eiffel Tower is tall to siphon the cold water. This pipe must withstand powerful currents and the immense pressure of the deep ocean. The initial capital costs are staggering, running into the hundreds of millions for a single, modest-sized plant. There are also environmental questions. What are the long-term effects of bringing vast quantities of cold, nutrient-heavy water to the surface and discharging slightly warmer water back into the ocean? Could this alter local ecosystems or even affect regional climate patterns over time? For now, the technology remains on the cusp, its potential gleaming just below the surface. Which vulnerable island nations, currently spending a crippling portion of their wealth on diesel fuel, could be the first to transform their economies with this steady, homegrown power? The ocean's thermal layers are not the only marine frontier offering a new kind of power. Another technology looks not to the water's temperature, but to the relentless, rhythmic motion of the waves themselves. The rhythmic pulse of the ocean extends far beyond its surface waves, reaching into the very geography of our coastlines. Tidal lagoons present a uniquely engineered solution, creating a predictable, artificial heartbeat of power. Picture an immense horseshoe-shaped wall built just offshore, enclosing a vast area of sea to form a calm, contained lagoon. This is not a dam blocking a river, but a reservoir for the tide itself. As the tide rises, water flows freely through tunnels in the seawall, spinning turbines to generate electricity as it fills the lagoon. When the tide falls, the water stored inside the lagoon rushes back out to sea, spinning those same turbines again. This cycle delivers 4 distinct bursts of power every single day, as reliable as the moon's orbit. The immense advantage, as championed by developers like Tidal Lagoon Power, is this utter predictability. We can forecast tidal movement centuries in advance, allowing grid operators to know exactly when this power will arrive, a stark contrast to the intermittency of sun and wind. The proposed Swansea Bay Tidal Lagoon in Wales is a blueprint for this future. Its seawall would stretch nearly 6 miles, creating a new recreational haven for sailing and water sports, while its turbines generate enough electricity for over 150,000 homes. Integrating this power into the grid is a matter of timing and storage, aligning its predictable output with daily energy demand peaks. The construction itself is a monumental task, using rock and concrete armoring similar to large breakwaters, designed to withstand a century of relentless marine punishment. Long-term maintenance involves managing the slow, inevitable scour of sediment and ensuring the turbines remain clear of marine debris. Yet, the most profound consideration lies beneath the water's surface. How can we balance this clean energy production with preserving the complex marine habitats we are building within? The seawall itself becomes an artificial reef, potentially attracting new marine life, but it also alters the natural flow of sediment and the migration paths of fish and marine mammals. Careful site selection is paramount, avoiding sensitive spawning grounds and designing fish-friendly turbines that minimize harm. This rhythmic, lunar-powered energy source demonstrates a profound truth. We are not just capturing nature's force, we are learning to dance with its tempo, a concept that takes on a different form when we look not at the coast, but deep underground where the planet's own inner fire awaits our call. The quiet merging of a river with the ocean is far more than a scenic wonder. It is a natural battery charged by a fundamental difference, the stark contrast between fresh water and salt. This meeting point holds a massive, untapped potential known as salinity gradient power, or blue energy. The principle is a beautiful application of natural physics. When fresh river water and salty seawater sit on either side of a special semi-permeable membrane, the water molecules from the freshwater side naturally move through the membrane to dilute the saltier side. This relentless flow is osmotic power in its pure form. The challenge for engineers is to harness that movement. In a system called pressure-retarded osmosis, this natural flow is channeled into a pressurized chamber on the seawater side, dramatically increasing the water pressure there. This high-pressure water is then released through a turbine, spinning it to generate electricity. It is a quiet, continuous process, generating power as long as the river flows into the sea. Professor Kitty Nijmeijer and her team at TU Eindhoven are at the forefront of this quest, designing next-generation membranes. The key is creating a material that is incredibly thin to allow high water flow, exceptionally robust to withstand constant pressure, and highly selective to block salt ions. It is a monumental materials science challenge. The potential integration points are what make this concept so compelling. Imagine a desalination plant, which already handles vast quantities of seawater and produces a brine byproduct. A blue energy plant could be built alongside it, using the plant's concentrated brine and a nearby freshwater source to create an even stronger salinity gradient, thereby generating extra power from an existing industrial process. This symbiotic relationship turns a waste stream into a valuable asset. We have already seen this principle in action. The Norwegian company Statkraft operated the world's first prototype osmotic power plant, proving the technology's fundamental feasibility. Meanwhile, in the Netherlands, a nation built upon managing the meeting of land and sea, pilot projects continue to refine the approach. The primary hurdle remains cost. The membranes are still expensive to produce at the scale and durability required for a commercial power station. This is where nanotechnology offers a glimmer of hope. Researchers are experimenting with atomically thin materials like graphene, which could create membranes with unparalleled flow rates and strength. What other innovation could tip the scales? Could biomimicry, copying the incredibly efficient membranes found in living cells, provide the blueprint for a commercial breakthrough? Mastering this gentle fusion of fresh and salt water reminds us that power often lies in the balance between elemental opposites, a principle that takes a dramatically different form when we look to the skies, where the sun's raw power meets the engineered perfection of a new kind of sail. Beneath our feet lies a furnace of unimaginable scale, a source of power that has fueled the planet's core for billions of years. This is the promise of enhanced geothermal systems, a technology that does not wait for nature to provide a hot spring or a geyser. Instead, it forges its own. The concept is audacious yet straightforward. We drill deep, sometimes miles down, into hot, dry rock that lacks the natural water or fractures needed for conventional geothermal power. Then we create a reservoir. High-pressure fluid is pumped down, delicately fracturing the deep rock to create a vast subterranean network of cracks. This artificial web becomes a heat exchanger. Water is then circulated through this man-made labyrinth, superheating as it travels, before returning to the surface as steam to drive turbines and generate electricity. The result is a power plant with a remarkably small surface footprint, operating 24 hours a day, completely unaffected by weather or the time of day. The United States Department of Energy's Geothermal Technologies Office sees this as a game changer, a way to unlock a domestic energy reserve that could supply the nation's needs for thousands of years, all with near zero emissions. The engineering, however, is as immense as the reward. We are essentially building a power plant in solid rock, thousands of meters underground. This requires advanced drilling technologies that can withstand extreme heat and pressure, borrowed and adapted from the oil and gas industry. This repurposing of expertise is a crucial bridge, turning the skills of a fossil fuel era toward a clean energy future. Managing the reservoir is its own intricate dance. Engineers must carefully monitor the flow of water and the stability of the fractures to ensure consistent heat extraction over decades. The landmark project at Sault-Sous-Forêts in France has demonstrated that this is not just a theory. For years, it has successfully generated power from a created reservoir, proving the long-term viability of the technology. But such deep earth engineering is not without its concerns. The process of fracturing rock can cause minor seismic shifts, tiny tremors that are usually too faint to be felt at the surface. Yet the question lingers. How can we guarantee to a nearby community that their homes will remain undisturbed? The answer lies in meticulous site selection, continuous monitoring with sensitive seismometers, and carefully controlling the fluid pressure used during stimulation. By listening intently to the whispers of the earth below, operators can adjust their operations in real time to prevent any significant activity. This assurance is the bedrock of public trust. Could this same deep earth prowess allow us to tap into even more extreme energy sources, where the planet's own tectonic fury is the fuel? The same deep earth prowess that creates artificial geothermal reservoirs could take us one step further, directly into the planet's fiery heart. Magma Power is the ultimate expression of geothermal ambition, where we do not merely harness hot rock, but drill directly into chambers of molten rock themselves. This is not a gentle heat exchange, it is a plunge into a superheated furnace. By tapping into a magma body, we can superheat water or another working fluid to extreme temperatures and pressures, creating steam far more powerful than anything from a conventional geothermal well. This superheated steam can then drive turbines with vastly greater efficiency, generating significantly more electricity from a single well. Volcanologist Dr. John Eichelberger has pointed out that accessible magma resources, often found in volcanically active regions like Iceland or parts of the United States, could provide immense power with an incredibly small physical footprint on the surface. The entire operation might look little different from a standard geothermal plant, but its subterranean reach is profoundly more daring. The key to this endeavor lies in materials science. What drill bit can possibly withstand direct contact with molten rock, which can exceed 1,200 degrees Celsius? The answer may lie in advanced ceramics and specialized alloys that resist both extreme heat and the corrosive chemistry of magma. The Iceland Deep Drilling Project provided a dramatic, if unplanned, proof of concept when their drill bit unexpectedly pierced a magma chamber at a depth of over 2 kilometers. Instead of a disaster, it became a windfall of data. They were able to pump water into the well, demonstrating they could generate high-pressure steam directly from the magma contact, a thrilling validation of the core principle. Beyond the drill bit itself, the entire well casing and the system for circulating fluid must be engineered to survive in what is essentially a man-made volcano. The energy conversion methods are equally critical. Standard turbines would be overwhelmed by the intensity of the steam produced. We would need to develop robust new turbine designs or use the magma's heat in a closed-loop system, where a secondary fluid with a very high boiling point circulates through pipes embedded near the magma, absorbing the intense heat without ever directly touching the molten rock. This indirect approach contains the risk but still captures the phenomenal energy. Yet, the most profound question surrounding magma power is one of safety. How do we monitor and manage the risk of inadvertently triggering a volcanic event? The technology demands an unprecedented network of seismic and gas sensors around the drill site, providing a real-time pulse of the underground environment. By understanding the subtle signs of unrest, engineers could adjust pumping pressures or even temporarily shut down the operation to prevent destabilizing the magma chamber. The reward is a nearly limitless, ultra-efficient energy source in specific regions. The risk is the sobering responsibility of interfacing with one of the planet's most primal and powerful forces. This dance with subterranean fire represents a threshold, a point where our energy ambitions meet the raw, untamed power of Earth itself. The sun's colossal power, born from the heart of a star, is a force we are now learning to recreate in laboratories here on Earth. Nuclear fusion promises to replicate this process, fusing light atomic nuclei together to release staggering amounts of energy. Unlike nuclear fission, which splits heavy atoms apart, fusion combines light ones, offering a fundamentally different profile. Its primary fuel, isotopes of hydrogen called deuterium and tritium, can be extracted from seawater and manufactured, presenting a virtually limitless supply. The reaction produces no long-lived radioactive waste and carries no risk of a runaway meltdown, positioning it as the holy grail of clean, dense power. For decades, however, the challenge has been profound. How do you build a star in a box? The answer lies in mastering plasma, a superheated gas where electrons are stripped from their atoms, creating a swirling fourth state of matter. To force atomic nuclei to overcome their natural repulsion and fuse, this plasma must be confined at temperatures exceeding 100 million degrees Celsius, far hotter than the sun's core. Two primary methods have emerged in this epic struggle to contain a star. The first uses immensely powerful magnetic fields to suspend and squeeze the plasma within a toroidal or donut-shaped chamber. This is the principle behind the tokamak, the most developed design, and its more complex but potentially more stable cousin, the stellarator. The second approach, inertial confinement, uses an array of incredibly powerful lasers to blast a tiny fuel pellet, compressing and heating it to fusion conditions in a microscopic, fleeting star. The progress in both fields has been accelerating. The joint European torus or JET has repeatedly broken its own records, generating significant fusion power and providing invaluable data. The International ITER project, a monumental collaboration of 35 nations, is building the world's largest tokamak in France, designed to be the first machine to achieve a net energy gain, producing more power from fusion than is used to heat the plasma. Meanwhile, private companies like Commonwealth Fusion Systems are pushing the boundaries with new high-temperature superconducting magnets. These revolutionary magnets can produce stronger magnetic fields in a smaller, more efficient machine, potentially shortening the path to a commercial reactor. Yet the path is still strewn with immense challenges. The fusion reaction bombards the reactor walls with a torrent of high-energy neutrons, degrading and embrittling even the strongest materials over time. Developing materials that can survive this relentless assault for years is a critical frontier. Some researchers are exploring aneutronic fusion, a different type of reaction that produces fewer neutrons and could drastically reduce radioactivity, but this requires even higher temperatures and remains a longer-term prospect. The ultimate question extends beyond physics and engineering. When fusion power finally becomes a reality, it will not merely be a new power source, it will recalibrate global politics. How will a world where any nation can access nearly limitless, clean energy from a glass of water reshape international relations, energy security, and economic power? This pursuit of stellar power on Earth represents our most ambitious technological endeavor, a testament to our desire to harness the universe's fundamental forces. But what if we could achieve a similar density of power on a much smaller, more distributed scale? A different kind of nuclear fission promises to rewrite the rules of atomic energy, not by abandoning the process, but by perfecting it with a slow, self-sustaining burn. Traveling wave reactors operate on a principle that seems almost biological in its elegance, a nuclear reaction that gradually consumes its fuel like a slow-burning ember. The core is initially loaded with a vast quantity of depleted uranium, a byproduct of the enrichment process that is considered nuclear waste. A small amount of enriched fuel is placed at one end to ignite the reaction. From this spark, a wave of nuclear fission begins. As neutrons from the reaction strike adjacent atoms of depleted uranium, they transmute them into plutonium-239, which itself becomes fissile fuel. This newly created fuel then ignites, propagating the wave of fission slowly through the core. It is a reactor that breeds the vast majority of its own fuel as it operates, a closed-loop system that could run for 40, 60, or even more years without ever needing to be refueled. The innovation lies in the neutron economy, a careful balancing act where just enough neutrons are produced to sustain the chain reaction while converting the next layer of fuel. This is not a fast, explosive process but a controlled, creeping burn managed with precision physics. Companies like TerraPower, co-founded by Bill Gates, are pioneering this technology with designs that emphasize inherent safety. The reactor relies on passive safety features where the laws of physics themselves prevent a meltdown. If the core overheats, the fuel expands, which naturally slows the nuclear reaction and brings the temperature back down, all without any need for operator intervention or powered safety systems. This dramatically reduces the risk of accidents. The fuel cycle itself is a form of alchemy, turning a waste product into a valuable asset. The world's stockpiles of depleted uranium, currently seen as a liability, could power entire nations for centuries. Furthermore, the specific nature of the reaction in a traveling wave reduces the production of the most long-lived and problematic isotopes found in traditional nuclear waste, simplifying the final disposal problem. The economic argument is compelling. A power plant that requires refueling only once in its multi-decade lifespan has vastly reduced operational costs and fuel supply chain complexities. Projects like the Natrium reactor planned for Wyoming aim to demonstrate this combined value, pairing a traveling wave-like advanced reactor with a molten salt energy storage system to provide flexible, dispatchable power that can complement renewable sources. Yet the path to deployment is not just a technical one. What regulatory frameworks must adapt to certify a reactor that runs for half a century on a single fuel load? How do inspectors verify the integrity of a sealed core over such an immense timescale? These are the profound questions that must be answered before this wave of fission innovation can truly break ground. This idea of a self-perpetuating energy system finds a remarkable parallel in the living world, where the simplest organisms have been running on their own perfect fuel cycles for billions of years. Microscopic green organisms could hold the key to fueling our existing vehicles and industries without altering a single engine. Algae biofuels transform simple ingredients, sunlight and carbon dioxide, into dense, energy-rich oils through the natural process of photosynthesis. The magic lies in specific strains of algae that are naturally prolific producers of lipids, the raw material for creating biodiesel, biojet fuel, and even biogas. Unlike traditional biofuel sources like corn or soy, algae does not compete for precious farmland. As Dr. Yusuf Kisti has extensively documented, these microorganisms can achieve astonishing growth rates, doubling their biomass in a matter of hours, and they flourish in environments where food crops cannot, such as arid non-arable land irrigated with wastewater or even seawater. Cultivating this green gold happens in two primary systems. Open ponds are vast, shallow raceways where algae grows exposed to the sun, a low-cost method that is simpler but vulnerable to contamination from other species. For more controlled and intensive production, engineers use photobioreactors, intricate networks of transparent tubes or panels that allow for precise management of light, temperature, and nutrients, leading to much higher yield. Once the algae has matured, the challenge becomes harvesting these tiny cells from their watery home. Techniques range from centrifugation, which spins the water at high speeds to separate the algae, to using flocculants that make the cells clump together and sink for easier collection. The final step is conversion, where the harvested biomass is processed into usable fuel. A promising method called hydrothermal liquefaction mimics the geological conditions that created fossil fuels, using high heat and pressure to transform wet algae into a crude bio-oil in a matter of minutes instead of millions of years. The brilliance of this system extends far beyond the fuel itself. The leftover biomass after the oil is extracted is a protein-rich slurry that can be sold as a high-quality animal feed, creating a secondary revenue stream. Furthermore, every pound of algae grown actively consumes carbon dioxide from the atmosphere. This opens the door for a powerful synergy, where algae farms are co-located with power plants or factories, capturing their carbon emissions directly and turning a waste product into a valuable resource. The proof is already growing in ponds. Companies like Sapphire Energy have operated commercial-scale farms that successfully produce a renewable crude oil replacement, demonstrating that the entire process chain is technically viable. Yet the central question remains: how can we scale these green ponds to a level that meaningfully displaces a significant portion of the world's fossil fuel consumption? The hurdles are economic and logistical, involving reducing the energy required for harvesting and processing while finding ever more productive strains of algae. This organic energy pathway, powered by nature's simplest architects, blooms into our next concept, where we look to another natural system that operates on an entirely different timescale. Nature's most elegant energy solution has been operating in plain sight for billions of years, a quiet miracle in every leaf. Now, science is learning to replicate that process, not with biology, but with advanced chemistry. Artificial photosynthesis aims to build synthetic leaves, devices that use sunlight to transform water and carbon dioxide directly into storable fuels like hydrogen or liquid hydrocarbons. This creates a perfect closed-loop energy cycle. The sun provides the power, and the fuel produced releases only the carbon dioxide that was initially captured, achieving a truly carbon-neutral system. The heart of this technology lies in a delicate dance of light and chemistry. It begins with a light-absorbing material, often a semiconductor similar to those in solar panels, that captures photons from sunlight. This energy generates electrical charges that drive two separate chemical reactions on the surface of catalysts. One set of catalysts uses these charges to split water molecules into their core components, oxygen and hydrogen. The hydrogen can be captured as a clean fuel itself. Simultaneously, another set of catalysts uses the remaining energy and charges to convert carbon dioxide from the air into more complex hydrocarbon fuels like methanol or even ethanol. This is where the work of pioneers like Professor Daniel Nocera has been so transformative. His team developed robust, inexpensive catalysts made from abundant elements like cobalt and phosphate that can operate efficiently in ordinary water, even impure water, under benign conditions. This bypasses the need for rare, expensive metals like platinum, making the entire system far more practical and scalable for global use. The vision extends to system integration, where these synthetic leaves operate continuously, perhaps floating on ponds or integrated into building facades, pulling moisture from the air and carbon dioxide from the atmosphere to quietly produce fuel throughout the day. The potential for decentralized energy is profound. How might this technology empower off-grid communities? A remote village could have arrays of these artificial leaves producing liquid fuel from sunlight and air, powering generators for electricity or fueling vehicles without any need for a fragile supply chain. The fuel itself becomes the battery, storing solar energy in a dense, transportable chemical form for use at night or during cloudy weather. This synergy with carbon capture is equally compelling. Imagine artificial photosynthesis units installed directly at industrial sites, using their waste carbon dioxide emissions as a raw material for fuel production, effectively turning a pollution problem into a power solution. Research hubs like the Joint Center for Artificial Photosynthesis in the United States have already demonstrated prototype systems that achieve impressive efficiencies, proving the core science is sound. The remaining challenges are about engineering and economics, refining the materials for longer lifetimes and higher conversion rates to make the fuel cost competitive. This brilliant mimicry of nature's oldest trick invites us to reconsider energy storage not as an engineering problem, but as a chemical one. If we can bottle sunlight in a fuel, what other fundamental processes of our world could we learn to replicate for limitless power? The elegance of artificial photosynthesis transforms sunlight into fuel, but that stored chemical energy is only one side of the equation. We must also find ways to bank the raw electricity flowing from our solar panels and wind turbines, and for that, we can turn to one of the most fundamental forces in the universe. Gravity itself can become a colossal battery, using the simple act of lifting and lowering a heavy weight to store and release power. When the sun is shining and the wind is howling, surplus electricity drives massive motors to hoist enormous blocks of concrete high into the air. In that elevated position, the blocks hold potential energy, a promise of power waiting to be fulfilled. Then, when demand spikes or the sun sets, the brakes are released. The controlled descent of those immense weights spins generators, converting that stored potential back into electricity and feeding it directly into the grid. This is the principle of gravitational potential energy, a lesson from high school physics scaled up to an industrial magnitude. The beauty of this system is its stunning simplicity and longevity. Unlike chemical batteries that degrade over thousands of cycles, a concrete block or a body of water can be raised and lowered for decades with virtually no loss of its inherent capacity. The core challenge is not the physics but the infrastructure. Where do you build such a thing? For generations, the most successful implementation has been pumped hydro storage. Facilities like the Dinorwig power station in Wales use two reservoirs at different elevations. During times of low demand, cheap electricity pumps water to the upper lake. When the UK needs a sudden surge of power, valves open and water cascades down through tunnels to spin turbines in an underground cavern, going from zero to full power in a matter of seconds. This is a proven, powerful technology, but it is geographically limited. You need the right kind of mountainous terrain with two large bodies of water. This limitation has sparked a new wave of innovation aimed at making gravity storage accessible anywhere. Companies like Energy Vault are reimagining the concept with monumental crane systems that autonomously stack and unstack 35-ton composite blocks into towering structures. These automated warehouses for potential energy can be built on flat land, using local soil or even recycled waste to form the blocks themselves. The economic argument is compelling when you consider the full lifespan. While a lithium-ion battery farm may need complete replacement every 15 or 20 years, a gravity system's primary components are mechanical, designed to last for 50 years or more with basic maintenance. This makes the long-term cost of stored energy remarkably low. The search for viable sites is also leading to creative repurposing. Abandoned mine shafts which plunge deep into the earth present a ready-made vertical drop. Imagine a system where surplus power lowers a massive weight down a disused mine shaft, and then during peak hours, that weight is allowed to rise, generating electricity as it ascends. This gives a productive second life to otherwise derelict industrial sites. The materials themselves are another advantage. There are no rare earth elements, no toxic electrolytes, and no fire risk. At the end of its life, a concrete block can be crushed and recycled, a stark contrast to the complex environmental challenges of battery disposal. This weighty solution offers a foundational pillar for a renewable grid, a way to smooth out the unpredictable pulses of nature with the steady, reliable pull of the earth. What other untapped movements in our world could we harness to keep the lights on? Deep underground, immense forces wait in silence, holding the potential to power entire cities with nothing but pressurized air. Compressed air energy storage, or CAES, turns surplus electricity into an invisible, physical battery. When wind and solar produce more power than the grid needs, that excess electricity drives massive compressors, forcing air into vast underground caverns. These are not man-made tanks, but natural geological formations like salt domes, excavated salt caverns, or porous rock aquifers sealed by impermeable caprock. The air is squeezed to incredible pressures, storing the energy of the gale or the sunbeam as potential force. Then, when demand surges and renewables fall quiet, valves are opened. The high-pressure air rushes out, heated and mixed with a small amount of natural gas to drive expansion turbines that generate electricity, feeding it back to the grid in minutes. This system provides a colossal, long-duration reservoir for power, capable of supplying hundreds of megawatts for many hours or even days. The key to efficiency lies in managing the heat. Compressing air makes it extremely hot, and traditional CAES plants simply let this heat dissipate, wasting a huge amount of energy. Advanced adiabatic designs, as researched by teams at the Pacific Northwest National Laboratory, solve this. They capture the intense heat of compression in a thermal store, like a bed of rocks or a specialized fluid. When the air is released, this stored heat is used to re-warm it before it enters the turbine, drastically reducing or even eliminating the need for supplemental natural gas. This makes the entire cycle far more efficient and truly clean. The McIntosh facility in Alabama stands as a testament to the durability of this technology, having provided reliable grid support since the 1990s. It uses a solution-mined salt cavern over 2,000 feet underground, demonstrating the remarkable stability of these natural vaults. The hunt for suitable geology is a global endeavor. How do we identify the right sites? Geologists use seismic surveys to map subsurface structures, looking for the specific characteristics of salt formations or verifying the integrity of a porous aquifer's seal. This pressurized approach is not just about storage, it is about creating a symbiotic relationship with renewable sources. A wind farm paired with a CAES plant becomes a far more reliable and dispatchable power source, its erratic output smoothed into a predictable supply. The very air we walk upon becomes a strategic energy reserve, a hidden landscape of power waiting for its moment to expand and drive our world forward. The silent, invisible battery of compressed air finds a dramatic counterpart in a technology that stores power as pure, tangible motion. Massive flywheels spin in near-perfect vacuums, their rotors levitating on magnetic bearings to eliminate mechanical friction. These are not simple spinning disks, but sophisticated kinetic energy reservoirs. When the grid has excess power, an electric motor accelerates the rotor to incredible speeds, sometimes exceeding 50,000 revolutions per minute, storing electricity as rotational energy. When the grid needs a sudden burst of power, the process reverses, the flywheel's inertia spinning a generator that feeds electricity back almost instantaneously. This ability to absorb and discharge power in milliseconds is their superpower, making them ideal for frequency regulation. The grid's frequency must remain perfectly stable, typically at 60 Hz in North America. If a large power plant suddenly goes offline or demand spikes, the frequency dips. Flywheel farms, like those pioneered by Beacon Power, can inject power into the grid within seconds to correct these tiny but critical fluctuations, preventing brownouts and protecting sensitive equipment. The engineering marvel lies in the details. The rotor itself is a masterpiece of materials science, often woven from carbon fiber composites that are incredibly strong yet lightweight, able to withstand immense centrifugal forces without flying apart. The entire assembly is sealed inside a vacuum chamber to eliminate air resistance, the last remaining source of drag. The magnetic bearings are the final touch, creating a frictionless suspension so the rotor can spin for days with only minimal energy loss. This combination gives flywheels a phenomenal lifespan, capable of millions of full charge and discharge cycles without any degradation, a stark contrast to chemical batteries which wear out after thousands. The environmental footprint is equally minimal. There are no toxic chemicals, no rare earth metals, and no thermal runaway risk. At the end of its decades-long service life, a flywheel is primarily steel and carbon fiber, materials that are straightforward to recycle. This makes them a clean, resilient anchor for critical infrastructure. Their application extends far beyond the grid. In data centers, where a millisecond power glitch can crash entire server farms, flywheels provide an uninterruptible power supply, bridging the critical gap before backup generators spin up. In transportation, they capture the energy from braking trains and buses, storing it to provide a burst of acceleration, improving efficiency. Even NASA harnesses this principle in spacecraft, where flywheels, known as control moment gyroscopes, are used for attitude control, their spinning mass gently orienting the station without expending precious propellant. The frontier now is energy density. What new materials could push flywheel performance to new heights? Researchers are exploring high-temperature superconductors for even more efficient magnetic levitation and nanomaterials that could allow rotors to spin even faster and store more energy in a smaller space. This spinning innovation whirls us into the realm of quantum energy, where the rules of physics itself are rewritten to unlock power. Our mastery of light reaches a new frontier within crystals smaller than a virus. Quantum dot solar cells are not merely an improvement on existing technology, they are a fundamental reinvention of the solar panel itself. These are nanoscale semiconductor crystals, so tiny that their physical size, not their chemical composition, dictates their electrical properties. By precisely controlling the diameter of each dot during synthesis, engineers can tune it to absorb a specific color of light. This is the power of band gap engineering. Imagine a traditional solar panel as a net that can only catch large fish, missing all the smaller ones. A quantum dot solar cell, however, is like a net woven with countless different mesh sizes, each designed to catch a different type of fish. This allows it to harvest a much broader spectrum of sunlight, from ultraviolet to deep infrared, that conventional silicon panels simply ignore. The real magic happens inside these tiny cages of light. Under certain conditions, a single high-energy photon striking a quantum dot can generate not one, but two or even more electron-hole pairs, a phenomenon known as multi-exciton generation. This shatters a long-standing theoretical ceiling called the Shockley-Quasar limit, which has capped the maximum efficiency of traditional single-junction solar cells for decades. The work of pioneers like Professor Maungi Bondi at MIT has been pivotal, developing chemical synthesis methods that produce quantum dots which are not only highly efficient but also stable enough to withstand the rigors of real-world operation. These nanocrystals are typically applied to a surface using layer-by-layer deposition techniques, building up a light-absorbing film one precise molecular level at a time. This opens up astonishing new forms for solar technology, because the dots can be suspended in liquid and printed onto almost any surface. We could soon see solar cells that are flexible enough to be woven into clothing or rolled up like a mat. They can also be made semi-transparent, transforming everyday windows into subtle power generators without obscuring the view. Recent laboratory efficiencies have already surged past 18%, a clear signal that this is no longer just a lab curiosity, but a technology on the cusp of commercial reality. The push now is to solve the challenges of scaling up manufacturing, ensuring every batch of billions of dots is perfectly uniform, and moving toward non-toxic materials like certain perovskite variants to replace older compounds containing heavy metals. One of the most promising near-term applications is not to replace silicon, but to partner with it. A thin film of quantum dots could be layered on top of a standard silicon cell, capturing the high-energy blue and ultraviolet light that silicon struggles with, while letting the red and infrared light through for the silicon to absorb. This tandem approach could quickly push commercial panel efficiencies to unprecedented levels. How will quantum dots change the aesthetics and application of solar energy? The answer points to a future where solar collection is no longer confined to bulky, blue-black rectangles on rooftops, but becomes an integrated, nearly invisible part of our built environment, from the glass facades of skyscrapers to the sunroof of your car. This nanoscale manipulation of light finds a powerful resonance in a concept that manipulates an entirely different form of radiation. The very windows of our buildings could soon become quiet power plants, subtly converting the sun's glow into usable electricity. Luminescent solar concentrators achieve this magic not with opaque panels, but with transparent or tinted sheets infused with special light-absorbing molecules. These sheets act as light traps. When sunlight strikes them, the embedded dyes or quantum dots absorb the light and then re-emit it at a longer wavelength. This re-emitted light is then guided or channeled toward the thin edges of the sheet by a phenomenon known as total internal reflection, the same principle that keeps light traveling along a fiber optic cable. At these edges, narrow strips of conventional, highly efficient solar cells wait to capture this concentrated light and transform it into electrical current. The key breakthrough, championed by researchers like Dr. Michael Debige at Eindhoven University of Technology, lies in the stability and performance of the light-absorbing materials or fluorophores. Early versions degraded quickly under constant ultraviolet exposure, but modern organic dyes and carefully engineered nanoparticles can now withstand years of direct sunlight without significant loss of intensity or color. The central design challenge is a beautiful trade-off. How do you balance the desire for a perfectly clear window with the need to capture as much light as possible? A highly transparent LSC might let 95% of the visible light through for illumination, while a slightly more tinted version could capture more energy, creating a power-generating sunroof or skylight. This dual functionality unlocks applications far beyond office towers. Consider the vast glass surfaces of modern agricultural greenhouses. Standard solar panels would block the specific wavelengths of light that plants need for photosynthesis, but a carefully tuned luminescent solar concentrator can be designed to absorb only the green light that plants largely reflect, converting that wasted energy into electricity to power the greenhouse's climate control and lighting systems, while letting all the beneficial red and blue light through for the crops. This elegant synergy extends to our vehicles. A car's panoramic glass roof could generate enough power to run the air conditioning or extend the range of an electric vehicle, all while providing shade and comfort. In the Netherlands, the company Piezoelectric has installed its power windows in commercial buildings, where the vertical glass facades generate power without altering the building's sleek architectural aesthetic. The potential for low-cost urban deployment is staggering. Since the primary material is a simple plastic or glass sheet, manufacturing could be scaled rapidly using existing industrial processes for windows and laminates. Imagine entire city skylines not studded with black rectangles, but made from the very glass and clear surfaces that define them, passively harvesting energy throughout the day. How can LSCs transform our cities into power-generating landscapes? This transparent technology weaves energy harvesting directly into the fabric of our lives, a quiet revolution happening right before our eyes. Every step you take could soon be a tiny power plant in disguise. Piezoelectric energy harvesting transforms the simple, constant vibrations of our daily lives into a source of electricity. It all comes down to a special class of materials, crystals, and certain ceramics and polymers that generate a small electric charge when they are squeezed, bent, or placed under mechanical stress. This is the direct piezoelectric effect, a phenomenon where physical pressure creates electrical power. The applications are as diverse as they are ingenious. Researchers like Dr. Henry Sedano at the University of Utah are developing these materials to create self-powering systems. Imagine wireless sensor networks spread across a smart city, monitoring air quality or structural health in bridges, all powered indefinitely by the rumble of passing traffic or the subtle sway of the structure itself. eliminating the need for costly and disruptive battery replacements. The science hinges on pushing the boundaries of material durability and efficiency. These piezoelectric elements must withstand millions of cycles of stress, from the relentless pounding of truck tires on a highway to the constant patter of feet on a subway station floor. Advanced polymers and composite materials are being engineered to be both highly responsive and incredibly resilient, capable of operating for years buried within our infrastructure. We are already seeing this in action on a surprising scale. The East Japan Railway Company has installed piezoelectric pads in the floors of its ticket gate turnstiles. Every single time a passenger steps through, their footfall creates a small pulse of electricity, which is harvested to help power the station's lighting and displays. In nightclubs from London to Rotterdam, piezoelectric dance floors capture the energy of dancers, converting their movements into a pulsating light show that is literally fueled by the rhythm of the crowd. The environmental appeal is profound. Once installed, these systems are virtually maintenance-free, generating power silently and without any emissions for the entirety of their long operational life. They represent a form of passive energy recycling, capturing kinetic energy that would otherwise be wasted as heat and vibration. This invites a fascinating question. Could the collective energy of a bustling city sidewalk one day help charge the electric buses that run along it? The potential extends from the macro scale of highways down to the micro scale of your own clothing, where piezoelectric fibers woven into fabric could one day generate power from your movements to charge a phone in your pocket. This vision of drawing power from the world's constant motion flows seamlessly into a technology that cuts the final cord, transmitting energy not through wires but through the empty air itself. The final cord connecting us to our devices may soon vanish into the air itself. Wireless power transmission is turning empty space into a conduit for energy, promising a world free from tangled cables and dying batteries. This is not science fiction, but a practical application of resonant electromagnetic coupling. The principle is a delicate dance of tuned magnetic fields. A transmitter coil resonating at a specific frequency creates an oscillating magnetic field. A receiver coil, tuned to that exact same frequency, can efficiently absorb that energy, even over distances of several meters, while objects and people outside that resonant frequency remain largely unaffected. This near-field technique is the foundation for companies like Tricity, which is bringing systems to market that can charge electric vehicles simply by parking over a pad, or power consumer electronics from across a room. The vision extends beyond our living rooms. Imagine electric vehicles charging not just in your garage, but while driving on specially equipped roadways, their batteries constantly topped up by an invisible energy stream flowing from the asphalt. This technology also holds profound promise for the medical field. Implanted devices like pacemakers or neural stimulators could be powered continuously from outside the body, eliminating the need for risky replacement surgeries when their internal batteries run out. Safety is, of course, a paramount concern. International standards for human exposure to electromagnetic fields are rigorously applied, ensuring that the power levels used for these near-field systems are well within established safety limits, posing no more risk than the wireless signals that already surround us. A different approach, far-field wireless power, uses focused radio waves or lasers to send energy over much longer distances, like the COTA system by OSHA. This system can deliver a trickle charge to multiple devices like phones and sensors anywhere in a room, automatically tracking them and directing power like an invisible butler. The efficiency of these far-field systems is being supercharged by metamaterials, engineered structures that can bend and focus electromagnetic waves in once impossible ways. creating tight energy beams that minimize waste. How will this cordless reality reshape our daily lives? Our relationship with energy would become seamless and effortless, integrated so deeply into our environment that we would stop thinking about charging altogether. This invisible grid of power could drastically reduce the mountains of electronic waste generated by disposable batteries and proprietary chargers. When every device is powered by the same ambient energy field, the need for cords and individual power adapters simply disappears. This vision of energy flowing freely through the air connects to a different kind of power system, one that does not generate electricity, but intelligently manages its every movement. Superconducting grids promise to replace our creaking electrical arteries with silent, frictionless highways for power. This 20th concept hinges on a material's ability to carry immense electrical currents with zero resistance, a state achieved when certain compounds are cooled to cryogenic temperatures. Imagine transmitting electricity from a solar farm in the desert to a city 1,000 miles away without losing a single watt of power along the journey. That is the revolutionary potential of superconducting cables. Unlike conventional copper lines, which can waste up to 10% of the electricity they carry as heat, these super-cold conduits eliminate this loss entirely, transforming the economics of long-distance power transmission. The key to making this practical lies in the development of high-temperature superconductors, as Dr. Venkat Selvamanikam at the University of Houston has demonstrated. These are not high temperatures in the everyday sense, but rather materials that achieve their superconducting state when cooled with relatively inexpensive liquid nitrogen, around -196 degrees Celsius, instead of the far more costly liquid helium. His team pioneers the manufacture of these materials as flexible, tape-like wires, making them easier to deploy in real-world grid projects. One of the most compelling demonstrations of this technology is already operating in Essen, Germany. The Amper City project replaced a conventional high-voltage line in the city center with a 1-kilometer-long superconducting cable. This single, compact cable, no thicker than a man's arm, can carry the same amount of power as a traditional cable bundle that would be 10 times its size, all while fitting neatly into existing underground conduits and freeing up valuable urban space. The implications for renewable energy are profound. How can superconductors help balance intermittent renewable sources? Consider a massive offshore wind farm in the North Sea. Its power output is sporadic, surging when the wind blows and falling calm when it does not. A superconducting cable laid across the seabed could instantly and efficiently deliver that power to multiple countries, allowing a surplus of wind energy in one nation to compensate for a lull in another. This creates a resilient, continent-scale web where clean energy can flow to where it is needed most, smoothing out the natural fluctuations of sun and wind. The grid stability benefits are equally transformative. Superconducting cables have an innate ability to limit fault currents, those dangerous power surges that can occur during a lightning strike or equipment failure. They act as intelligent shock absorbers for the grid, preventing localized problems from cascading into widespread blackouts. The economic impact of eliminating transmission losses alone would be staggering, saving billions of dollars annually and making clean energy more affordable. This vision of a perfectly efficient, interconnected energy network inevitably raises a critical question. How do you manage the immense, dynamic flow of power across such a vast and intelligent web? The answer lies not in cables, but in a digital mind capable of overseeing the entire system. A silent, digital mind now watches over the flow of electricity, transforming our aging grid from a passive conduit into a dynamic, self-healing organism. This is the promise of AI-optimized energy networks, where artificial intelligence becomes the ultimate grid operator. It processes a torrent of data in real time, from satellite images of cloud cover to the minute-by-minute energy use of millions of smart meters. Machine learning algorithms analyze these patterns, forecasting electricity demand with astonishing accuracy and automatically balancing supply from a chaotic mix of solar farms, wind turbines, and conventional power plants. The result is a system that not only reacts to problems but anticipates them, preventing blackouts before they can even begin. The prowess of this digital brain was famously demonstrated by Google's DeepMind, which applied its AI to manage the energy-hungry cooling systems in its data centers. The system learned the complex thermal dynamics of the buildings and optimized cooling in real time, achieving a staggering 40% reduction in energy used for cooling. This was not a simple thermostat adjustment, but a deep, predictive understanding of how energy moves and can be conserved. The core of this intelligence lies in neural network architectures that mimic the human brain's ability to recognize patterns. These networks are trained on historical data, learning the subtle correlations between, for instance, a sudden drop in temperature, the start of a popular television show, and the resulting spike in power demand. They integrate live data from a vast Internet of Things, or IoT, including smart inverters on home solar systems, voltage sensors on power lines, and even electric vehicle charging stations. This constant pulse of information allows the AI to see the grid as a living, breathing entity. Crucially, this hyperconnectivity demands an unbreakable shield. Cybersecurity becomes the grid's immune system, with advanced encryption and continuous threat monitoring protecting these vital digital pathways from malicious attacks. This intelligent management empowers entirely new relationships with energy. Demand response programs like those run by companies such as Ohm Connect turn consumers into active grid participants. You might receive a notification that the grid is stressed on a hot afternoon, offering you a financial incentive to temporarily dim your smart lights or delay running your dishwasher. This collective, minor adjustment across thousands of homes acts as a virtual power plant, averting the need to fire up a polluting peaker plant. The AI also enables predictive maintenance, analyzing vibrations and thermal data from transformers to alert utility crews to replace a failing component weeks before it would have burst into flames and caused an outage. It even facilitates peer-to-peer energy trading, where your neighbor with rooftop solar can automatically sell their excess power directly to you, with the AI handling the billing and grid logistics seamlessly. How will this technology empower you to become an active trader in the energy market, not just a passive bill payer? This intelligent orchestration of electrons finds its perfect partner in a technology that stores power not as chemistry or motion, but as pure information in a computational engine. This digital ledger could become the foundation for a truly democratic energy system. Blockchain technology allows neighbors to trade solar power directly, cutting out the traditional utility middleman. Imagine your rooftop solar panels producing more electricity than you need on a sunny afternoon. Instead of selling that excess back to the grid for a low credit, you could offer it directly to the family down the street, perhaps at a price you both agree is fair. A blockchain is essentially a secure, transparent, and unchangeable digital record book. Every transaction, every kilowatt-hour traded, is recorded in a shared ledger that everyone in the network can see and trust, but no single person can alter. This eliminates the need for a central authority to verify the sale. Dr. Gemma Green, co-founder of Power Ledger, has been a pioneer in this space, creating platforms that turn energy into digital tokens. These tokens represent real power, and they can be traded instantly between people, with the blockchain automatically handling the secure transfer of ownership and payment. The magic that makes this work lies in smart contracts. These are self-executing digital agreements. You could set up a smart contract that automatically sells your excess solar energy to your neighbor whenever your battery is full, at a pre-agreed price. The moment the conditions are met, the trade happens, the ledger updates, and the payment is transferred, all without you lifting a finger. This entire system relies on a consensus mechanism, where multiple computers in the network must all verify and agree that a transaction is valid before it is permanently added to the chain. This decentralized validation is what makes the system so secure and tamper-proof. The Brooklyn microgrid in New York is a living example of this future in action. Residents with solar panels can choose to sell their power to other local participants through a blockchain-based platform, keeping the energy and the economic benefits within the community. This creates resilient microgrids, smaller networks that can often operate independently from the main grid. During a widespread blackout, a community microgrid powered by local solar and batteries could keep its lights on, its water pumps running, and its communication lines open. By generating and consuming power locally, these microgrids drastically reduce the immense costs and energy losses associated with transmitting electricity over hundreds of miles of power lines. This movement transforms ordinary homeowners into prosumers, a blend of producer and consumer. They are no longer passive bill payers but active participants in a new energy democracy, empowered to control their own power sources and their economic destiny. Yet, this decentralized approach raises a critical question for regulators. What new rules are required to ensure these peer-to-peer markets are safe, fair, and accessible to all? How do we modernize electricity regulations that were written for a centralized, one-way flow of power to accommodate a dynamic, multidirectional energy web? The answers will determine how quickly this empowering technology can scale, shifting power literally and figuratively back into the hands of communities. This vision of local, shared energy finds a powerful echo in our next concept, which tackles one of the most persistent challenges of the modern world. A quiet revolution in energy is rebuilding our systems from the neighborhood up. Community microgrids transform clusters of homes and businesses into self-sufficient energy islands, capable of disconnecting from the main grid during a storm or blackout and powering themselves with local sun, wind, and batteries. This is not just backup power, it is a fundamental rethinking of resilience. The Rocky Mountain Institute champions these systems as vital tools for climate adaptation and energy equity, ensuring that when the larger grid fails, critical services like water pumping, medical equipment, and communication remain online. The design principle is one of intelligent diversity. A single technology is a point of failure, so a robust microgrid combines solar panels, small wind turbines, battery storage, and sometimes a backup generator fueled by biogas or biodiesel. This hybrid system ensures that if the sun does not shine for a day, the batteries can discharge, and if the wind is calm for a week, the generator can fill the gap. The entire network is managed by a sophisticated brain, a microgrid controller that constantly monitors energy supply and demand, deciding when to draw from batteries, when to generate power, and when to seamlessly island itself from the main grid. The financing and governance of these projects are as innovative as the technology itself. How do you pay for a shared resource that benefits an entire community? Models range from utility-led development to community-owned cooperatives, where residents collectively invest in and govern their energy future. This collective ownership model, often structured as a legal entity like a limited cooperative, empowers residents to make decisions about their power sources, rates, and reinvestment of any profits back into the community. A powerful example of this synergy is the Borrego Springs microgrid in California. In this remote desert community, the local utility, San Diego Gas and Electric, integrated a large battery system with a nearby solar farm and a temporary generator. During a planned outage when the main transmission line needed repair, the microgrid successfully islanded and powered the entire town, including its critical grocery store and cooling center, for nearly 10 hours. This proves the concept at a real-world scale, demonstrating that independence does not mean isolation. These localized networks also form the building blocks of virtual power plants. While a microgrid can disconnect to save itself, a virtual power plant is a cloud-based network that aggregates the distributed energy resources from hundreds or thousands of homes and businesses, their rooftop solar, their Powerwall batteries, their smart thermostats. This aggregated capacity can then be dispatched by the grid operator as if it were a single, large power plant, providing clean peak power when demand is highest. This brings us to a profound social question. How can microgrids bridge the energy access gap in underserved areas? For remote villages in developing nations or low-income urban neighborhoods, extending the main grid can be prohibitively expensive. A community microgrid powered by local renewables can provide immediate, affordable electricity, fostering economic development and improving quality of life without waiting for centralized infrastructure. This localized power paradigm, where control shifts from distant corporations to local hands, represents a final terrestrial step toward true energy democracy. It prepares us to contemplate a single, ultimate source, a power so fundamental it has been the engine of the cosmos since the beginning. The air around us holds an ocean of invisible potential, a resource we are learning to condense into both life-giving water and clean burning fuel. Atmospheric water generation turns the very humidity we feel into a dual-purpose wellspring, creating a self-contained cycle powered by the sun. These devices operate on a principle as ancient as a cold drink on a hot day: condensation. Some use a cooling process, chilling a surface below the dew point to coax moisture from the air, much like a high-tech dehumidifier. Others employ advanced desiccants, materials that act like super sponges, actively pulling water vapor from the atmosphere. The real breakthrough lies in the sponges themselves. Chemists like Dr. Omar Yaghai have engineered crystalline structures called metal organic frameworks, or MOFs. These frameworks possess an astonishing internal surface area, a labyrinth of molecular cages specifically designed to trap and hold water molecules, even in the dry, thin air of a desert. Once captured, this harvested water becomes more than just a drink. It is the feedstock for a miniature energy revolution. Through a process called electrolysis, a small amount of solar electricity can split the water molecules, separating them into their base elements, oxygen and hydrogen. The hydrogen can then be stored, ready to be used in a fuel cell to generate electricity on demand, or even combusted directly in a clean, modified engine. This creates a perfect closed loop. Sunlight powers the harvest and the splitting, and the resulting fuel provides power when the sun is gone. The implications for disaster relief are immediate and profound. Instead of waiting for massive shipments of bottled water and diesel fuel, a field hospital could deploy self-contained units that pull their own water from the air and generate their own electricity from it, achieving a level of operational independence that saves crucial time and logistics. This technology also fosters a powerful synergy with agriculture in arid regions. Imagine greenhouses in the desert where the panels on the roof not only provide shade but also generate the water for irrigation and the hydrogen fuel to power the pumps and climate control systems at night. Companies like Source Global are already making this a tangible reality with their hydropanels. which are providing clean drinking water for remote schools and communities from Arizona to Kenya, operating entirely off-grid. The scalability is a key feature, ranging from a single household unit that meets a family's daily water needs to vast industrial farms of collectors that could one day support whole cities. How might this address both water and energy scarcity simultaneously? It reframes the two crises as a single solvable equation, using the sun's constant energy to unlock the hydrological cycle itself, transforming atmospheric vapor into a liquid asset and a gaseous fuel. This atmospheric harvesting concept elevates our perspective to the final frontier. A celestial ring of power could one day encircle our world, not as a solid shell, but as a constellation of interconnected energy hubs. Orbital power rings represent the next logical evolution beyond solitary solar power satellites, forming a dynamic network in high orbit. Each node in this ring would be a massive, self-contained station, equipped with vast solar arrays, advanced energy storage banks, and powerful microwave or laser transmitters. These stations would be linked by a web of data and power lines, creating a resilient grid in the sky. This infrastructure would serve as the backbone for a true space economy, beaming gigawatts of power not only to Earth but also to lunar outposts, fuel depots, and spacecraft venturing deeper into the solar system. Visionaries like Dr. Joseph Pelton of the International Space University see this as the essential utility for humanity's expansion, a power grid for the inner planets. The engineering begins with orbital dynamics, placing these rings in stable paths where they are almost constantly in sunlight. Construction would be a symphony of robotics, with autonomous spacecraft assembling the colossal structures piece by piece, likely using materials harvested from the moon or nearby asteroids to avoid the immense cost of launching everything from Earth. This endeavor would demand unprecedented international cooperation, a shared project for all nations akin to the International Space Station, but on a far grander scale. How would we fairly govern the energy flowing from these shared orbital assets? The ethical considerations are profound, touching on everything from space traffic management to the prevention of one nation or corporation monopolizing the sun's output for itself. The applications extend far beyond our atmosphere. A Mars colony receiving only half the sunlight we enjoy on Earth could be powered by a steady, reliable beam from an orbital ring, enabling large-scale agriculture and industry on the red planet. For asteroid mining operations, these rings would provide the immense power needed to process raw ore and metals in situ, turning rubble into valuable construction materials without the need to fight a planet's gravity. This cosmic network forces us to confront our future as an interplanetary species. Will we carry our old rivalries and resource scrambles into the heavens, or will the sheer scale of this endeavor inspire a new era of collaboration? The answers will determine whether this ring of power becomes a symbol of unity or a new frontier for conflict, bringing our journey through these revolutionary concepts full circle to a future of truly endless possibilities. Our journey through these 24 energy revolutions reveals a future no longer defined by scarcity, but by extraordinary possibility. We have ventured from the planet's molten heart to orbital rings encircling our world, each concept a testament to human ingenuity and our enduring drive to harness the fundamental forces of the universe. This quest is about far more than technological mastery. It is a profound reimagining of our relationship with the planet and with one another, a shift from extraction to symbiosis, from centralized grids to distributed empowerment. As we stand at this pivotal threshold, the path forward will be illuminated not by any single invention, but by our collective will to collaborate, to invest, and to create. The conversation about our energy future is one we all share, I am eager to hear which of these concepts captured your imagination. Was it the silent spin of flywheels, the quiet condensation of fuel from air, or the audacious vision of a Dyson swarm? Let me know your thoughts in the comments below, and if you want to continue exploring the frontiers of tomorrow, be sure to subscribe. Together, we have the power to build a future that is not only brighter, but truly without